Hello and welcome to AP Physics 2.
Today we'll be talking about the photoelectric effect and the properties of waves and particles as we continue moving on with modern and nuclear physics. As always, we're going to start with a quick overview of the lesson, followed by our daily warm-up where we look at the question that we left off with yesterday. Then we'll move through what you need to know to be successful when it comes to answering questions about modern physics. Then we'll go through some guided practice as we look through questions the College Board has asked about these topics from the AP question bank. We'll do a quick debrief and summary, make sure that you picked up what we were putting down, and then we'll do some AP exam practice and leave you with something to work on for tomorrow. As always, I'm Joe Mancino. I teach at Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton. I teach at Reedy High School in Frisco, Texas. And so let's go over what we're going to be talking about today. First off, we'll start with the photoelectric effect, where we'll discuss such things as photon energy, work function, cutoff or threshold frequency, and conservation of energy and how that ties into those concepts.
And then we'll look at this idea of wave-particle duality. Again, we'll treat light like a wave and a particle, but we'll also talk about the ways that we treat matter as waves and particles. Specifically, we'll look at something called the Davison-Germer experiment. We'll look at how particles behave like waves on very, very small scales.
All right, and you should already know, at least we hope, that light behaves as a particle and a wave. You should know concepts such as current, voltage, and potential, and also kinetic energy for today's lesson.
And if we do our jobs right, by the end of this lesson, you will be able to identify the work function and the threshold frequency for a metal. You'll be able to determine the Debroglie wavelength of a particle, the wavelength of a particle.
And we'll be using these skills today. Articulations of the reasons that scientific explanations and theories are refined or replaced. You will be able to make claims and predictions about natural phenomena and connect concepts across topics.
That sounds great. All right, let's get started. We're going to pick up right where we left off yesterday. A bunch of hydrogen nuclei have combined together. They're going to form helium, and that's going to cause a fusion reaction, and lots of energy is going to be released. But what happens to the mass? Well, the products have less mass than the reactants. Now that may sound like it violates the conservation of matter, but that's because we've added a little twist. It's not just conservation of mass anymore, it's conservation of mass and energy. So the lost mass is converted into the energy of the particles. Now, asked a slightly different way, we left you with this question too. In our sun, nuclear reactions fuse together hydrogen, they make helium. What happens to the sun's mass over time? Well, it loses mass. It loses mass in the form of energy.
All right, to get your brains ready for today, here's your warm-up. So as you see, we've given you an energy level diagram for an electron in a hypothetical atom. And it says that a cold sample of gas of such atoms is illuminated by a brief flash of light with a continuous spectrum. These atoms are then observed to emit light with discrete wavelengths. Which of the following transitions produces the longest wavelength of light? I'll give you just a couple of seconds to think about that. But the thing that I'm going to point out is that it says the longest wavelength of light, the biggest wavelength of light. And I know that that corresponds to the smallest amount of frequency, which means the smallest amount of energy. So looking at those energy stages that you see between 1 and 2, 2 and 3, 3 and 4, 4 and 5, which one do you think has the smallest amount of energy change? Going by what we talked about yesterday, the smallest amount of energy change is going to be from 4 to 3, which also produces the longest wavelength of light.
Okay, so longest wavelength is lowest frequency, and least energy. Got it.
That's exactly it. So here's what you need to know from today. So photoelectric effect is basically just talking about certain metals, special metals that emit electrons when light is shined on them. And the energy from the photons can be transferred to the electron. And we'll also discuss how the work function describes how much work or energy is needed to eject an electron. And kind of remember that work and energy are basically the same thing. Now, with wave-particle duality, we need to know that particles have momentum, and also photons can have momentum, packets of light. With the Davis-Germer experiment, we need to know that it showed that electrons exhibit diffraction, and particles behave as waves on small scales. And shockingly enough, matter can also have a wavelength.
What? Okay, so matter has a wavelength. Light works like matter. This is getting weird. And here's where it gets weird. You may think that you know the most famous thing that Einstein ever did. You may guess why Einstein won the Nobel Prize. But I bet you're thinking E equals mc squared, maybe the most famous equation in all of physics, but it was actually for this, for explaining the photoelectric effect. Photo, light, electric, electricity. The photoelectric effect is the interaction between light and electrons, which is super weird. I see light shining on everything all the time, and I don't see electricity dripping off of me. Well, here's what's going on. In the photoelectric effect, light shines on a metal and electrons come off. So let me explain what you're going to see. Here you see it looks like a circuit with a great big gap in the middle. You see that there's positive potential on the right side, negative potential on the left side. If we shine light on whatever metal is in that sort of cup-shaped, C-shaped thing, electrons are liberated off of it and knocked over to the other plate. And that's weird. Shining light on a metal emits electrons from the metal. In 1887, Heinrich Hertz figured it out. He discovered that shining light just the right way on a metal makes electrons come off the metal, and that is weird. It's the first instance that we have of light interacting with matter. It's very mysterious. And no one could explain it for a while. 1887 until 1905, physics is left scratching their head about this. And it wasn't until then when Albert Einstein had an explanation. He said this: maybe light is made up of small particles. If you've been with us since the very beginning, you know that we started with the idea that the particle nature versus the wave nature of light was this huge question that physics was wrestling with. And until we understood the nature of light, we didn't really understand physics. So it wasn't until we had the wave nature of light explained and the particle nature of light explained that physics went from being classical physics to being modern physics. Here's how it works.
All right, so a metal surface, electrons are bound with a small amount of energy. And when light shines on that metal, some of the photons enter the surface, which again, photons are just packets of light, and they collide with the atoms of the metal and are totally absorbed. So when a photon gives its energy to an electron, which if the absorbed energy is great enough, the electron is able to break free from the atom. And basically, the photoelectric effect is the result of the collisions between those photons, the individual packets of light, and electrons that knock the electrons out of the metal. It's the entire process. But this effect only happens when the energy transported to an electron is roughly equal to the energy of a single photon.
Okay, whoa. Time out, Mr. Eaton. You're saying the word collision, but you're talking about light. Do you mean that light collides with electrons and the electrons bounce off like some kind of conservation of momentum experiment from AP Physics 1? That's crazy.
It is crazy. It is absolutely crazy.
It's
All right.
unintuitive, but again, nature is under no obligation to be intuitive.
It's just gotta be. All right, so let's talk a little bit about this photon energy that we've already kind of brought up just a little bit. So we have a basic equation that is energy is equal to hf. H is Planck's constant, and F is the frequency of the light. Now, H can be described a couple of different ways, and you just saw them on the screen. No big deal. Moving on. Moving on.
My apologies.
That's okay. That's okay. So there's two constants. No big deal.
I do want to point out, though, the units for Planck's constant are often expressed as joule seconds. If you look at the AP Physics 2 equation sheet, it says Planck's constant is 6.63 times 10 to the negative 34 joules seconds. I always like to write it as joules per hertz. It reminds me that Planck's constant describes the amount of energy per vibration. The idea that frequency carries energy. Joule seconds always loses the meaning for me. I think it's easier to type, but joules per hertz just looks nice.
It does look nice. All right. So if we go back to our basic wave equation that C is equal to F lambda, we can rearrange that pretty easily by saying that frequency is equal to the speed of light over lambda. So in this case, if E is equal to HF, we can rearrange the equation to say that E is equal to HC over lambda. And H and C are both constants in that equation. If we take both those constants and multiply them together, we get 1,240 electron volt nanometers.
That is a super useful number that you're going to want to write down. Planck's constant times the speed of light in useful units, those little units we talked about yesterday. H times C is 1,240 electron volt nanometers. Did you write it down? If you did, you'll be able to answer this. What's the energy in EVs of a 400 nanometer photon? Well, if energy is HC over lambda, and HC is 1240, it's 1240 over 400, 3.1 EVs. All right, the next question asks whether you can see a certain photon. Can you see a 2 EV photon? Well, 1240 over 2, that's 620 nanometers. 1,240 electron volt nanometers divided by 2 electron volts is 620 nanometers, and that is definitely in the visible range. It's that color. It's orange. So every metal can be described by one of its characteristics called the work function. The work function of a metal tells us how strongly the electrons are bonded to that atom. If a metal has a high work function, then it takes lots of work to pull the electrons off. The symbol for the work function of a metal is the Greek letter phi. So here are some work functions of various metals. There's sodium, zinc, cobalt, silver, and platinum. No need to memorize these. Just notice that they are on the order of between 1 and 10 for these metals. So those metals have a work function of between 1 and 10. For example, if you wanted to pull an electron off of zinc, it would take 3.9 electron volts of work to yank it off. So we shine light on a material and an electron comes off. Well, coming off means the electron has some kinetic energy. And the maximum kinetic energy with which that electron can be ejected, well, we follow the conservation of energy. It's related to how much energy the photon brings in and how much is left over after the photon has done the work function. So the incoming photon energy minus the energy cost of liberating that electron is the maximum amount of electron that's available, the maximum amount of energy that's available for that electron, or the maximum amount of kinetic energy that electron can have is the incoming photon energy, that's HF or HC over lambda, minus phi, that work function. So Mr. Eaton, you were saying that this is a lot like the conservation of energy. Talk us through that.
Absolutely. So the incoming photon has a certain amount of energy as described by one of the previous equations that we just talked about, which is HF. Now, if that incoming energy has just enough to overcome the work function, that's going to be equal to the total final energy of the electron. So initial energy plus the work done has to equal the total final energy. Again, just a basic statement of conservation of energy. So this leaves us with this final equation, which is HF is equal to kinetic energy plus phi. All right, let's see if you can calculate the maximum kinetic energy of an electron.
The maximum kinetic energy of that released electron. Well, it's going to depend on the energy of the incoming light and the work function. So, did you come prepared today? I know I did. The energy of the incoming light, well, it's 1240 divided by 95. I know how many electron volts that is, but I also know what the work function is. I know that we have to overcome that work function. We have to pay that much energy. I have my answer. Do you have yours? Well, if the maximum kinetic energy is hc over lambda minus the work function, I know that the energy of that incoming photon is 1,240 divided by 95, and the work function is 4.73 EVs. Did you get something in the neighborhood of 8 and change electron volts? Fantastic, or not. I can't hear you. We have no way to know what you're saying, but I believe in you. Try this one with the Mr. Eaton.
So let's try it with knowing what the kinetic or what the energy of the photon is instead of what the wavelength of the photon is. So if we have a photon that has 13 electron volts of energy, and the work function of that same piece of silver is 4.73 electron volts, let's see how that comes out. I know the kinetic energy has to equal the energy of the photon minus the work function. So this is even easier than the previous example. It's just 13 minus 4.73, which leaves us with a maximum kinetic energy of 8.3 electron volts.
Now, it's certainly easier if we just tell you the energy of the incoming photon, but that's unlikely to happen. If you'll be taking a high school test at your school on modern physics, you'll have to calculate the energy of the incoming photon, which means you'll need to say it's 1240 divided by the wavelength. But wait a minute. I get that this is going on. I get that shining light on a material makes electricity flow. I have solar panels on my house that are doing that right now. Thank you, sunshine. So is the photoelectric effect evidence of light's particle nature or of its wave nature? Well, let's take a look. So the initial explanations for the photoelectric effect had to do with the idea that maybe light is a wave that's shining on these metals and the metals are releasing electricity. And it makes some sense, a little bit, in terms of classical physics. If we shine, for example, blue light on a metal, it'll release some electrons with some kind of current I, and each electron will have an amount of energy E. Electrons are ejected with kinetic energy. And scientists realize that if they shine brighter light, that's light with a higher amplitude, we're thinking wave here, if they shine brighter light, well, that's more energy. So the ejected electrons should have more energy. Now, maybe that means more current, maybe that means more kinetic energy per electrons, and they were sort of right. Shining brighter light means a more energetic emission, but it left us with a riddle. So scientists tried it with brighter light. They tried it with light of longer wavelength. They tried it with brighter light of longer wavelength. So we'll discuss what happens if we shine all kinds of light on the same metal. So in the top right corner of your screen, you see a wave with a big amplitude, but the same wavelength, the same blue wavelength. If we shine those two kinds of light on a metal, the one on the left releases electrons with some kind of current, and the electrons have some energy. The wave on the right, the bigger amplitude, brighter light, it releases more electrons per second, but the electrons don't have a greater energy individually. There's more of them released, but the individual electrons don't have more energy. In the bottom left of your screen, you see light of the same brightness with a wider wavelength, a longer wavelength. That's lower energy light. It releases the same number of electrons per second, but each electron has less energy. Or if we shine bright light with a longer wavelength, the bright light releases more electrons, but those electrons don't have as much energy. Now, those four things taken together, they don't make sense given the wave model. You see, more energy should mean both more electrons that have more energy. The electrons shouldn't know how the energy is getting there. They should just have it. And then there's another anomalous behavior. If blue light is able to make a current and it's able to release electrons with energy, red light doesn't release any electrons. That's super weird. Orange light can do it. Even bright red light can't do it. And that doesn't make any sense. No matter how bright you make light, if it's too red, if it's too low energy, no electrons are emitted. There's no way to explain that with a wave. A big wave should be able to knock electrons off. But the particle model makes it make sense. Those two energetic photons release two electrons with lots of energy. It's a one-to-one correspondence. One photon hits one electron. Two photons hit two electrons. Sending more photons per second ejects more electrons per second, but blue photons can only emit electrons of a certain energy. Sending in orange photons, two of them, yeah, it releases two electrons. And those electrons have less energy, but it's still the same number. That red photon that you see, it doesn't have enough energy to pay the work function. Its lambda is too big, so its hc over lambda is too small. That red photon can't eject an electron. A lot of red photons can't eject any electrons either. No matter how many red photons we send, they don't eject electrons.
All right, so just like Mr. Mancino was saying, the intensity of light is just the brightness of the light, and it only means how many photons are being emitted by the light bulb itself. So very few photons, a whole lot of photons. That's it. It's not about the energy. So if the frequency is large enough of those photons, you can increase the intensity. The current increases because there will be more electrons ejected. And remember, thinking about circuits, when we went over circuits in class, the current is simply the number of electrons per second. That's all it is. So to continue summarizing on this, if light is shining on the metal and it has too low of a frequency, nothing happens, no matter how bright or how many photons are striking the surface of the metal. So the kinetic energy of the electrons is completely independent of the intensity of the light. Remember, energy is very much related to frequency, and intensity is very much related to the number of photons. So the more intense the light, more bright light, it can dislodge more electrons. So the current will increase in that case. But the kinetic energy is not going to increase. It's still capped at a value that we call kinetic energy max. So let's take a look at a quick graph, a little visual representation of what we're trying to say. So if you look at the graph, the y-axis has current and the x-axis has lambda, so wavelength. Now current is emitted only by wavelengths less than what we see on the right-hand side of lambda c. It's kind of a cutoff wavelength. Longer wavelengths are not going to cause current. So these represent that photons don't have enough energy to knock the electrons out of the metal. Anything past lambda c doesn't have enough energy to knock the electrons out of the metal. Because remember, when wavelengths get bigger, energy gets smaller. So for very small wavelengths, the light is not going to interact with the metal. So pretty much anything up towards the upper end of our electromagnetic spectrum that we talked about, X-rays, gamma rays, so on and so forth. All right, let's go back to this really quick. The light at the critical wavelength can dislodge electrons, but they don't have any kinetic energy. So if we look at our original equation, not our original equation, but we discussed this earlier, the kinetic energy is equal to hc over lambda minus the work function. But if the kinetic energy is 0 at lambda c, this is what that equation actually simplifies to. This is how you would solve to find the work function.
All right, so we're going to go back to that circuit-looking diagram where we're shining light on the metal and electrons are getting bumped off. Down there, that thing that looks like a battery, that's, imagine like a power source in your classroom that has an adjustable dial with adjustable voltage. If you can make that negative collector more and more and more negative, well, eventually those electrons are not going to be able to jump the gap. As the voltage is increased, the current slows down. That happens because the left plate, the negative one, becomes so negative, it keeps the electrons away. Only electrons emitted with really, really high energy from high energy light, only those electrons will cross the gap. So you can measure the maximum energy of the ejected electrons by looking at the voltage it takes to stop those electrons. At some voltage that you dial, called the stopping potential, no electrons make it to the collector. There is no current. But the stopping potential is independent of the intensity of light, and that is super weird for classical physics. This was impossible to explain before 1905. Even the brightest light did not change the stopping potential. So here's a graph of current versus stopping potential. As whatever experimenter turns up the voltage, eventually the current stops. At a high enough voltage, no electrons can jump that gap. The electrons are negative and the collector is negative, and there's just too much repulsion to overcome, or it's at too high a potential for the electrons to make the jump. The collector is negative, so the potential energy at the collector, it's just too high. The electrons can't get there. They didn't have enough kinetic energy. Or in order to arc across the gap, the kinetic energy of the ejected electrons must be greater than or equal to the potential energy. So at the stopping potential, at exactly the stopping potential, we know that the kinetic energy of the ejected electrons equals the potential energy of the collector, or K equals U, HF minus phi equals Q times V. Remember from electrostatics, Q times V is potential energy, which gets us to one more way to express the photoelectric effect. There it is. Energy is conserved. Charge times voltage, that's energy, is HF minus phi, where V is the stopping potential, H is Planck's constant, F is the frequency, phi is the work function, Q is the charge of an electron. All right, that works because at the stopping potential, the potential energy is the same as the maximum kinetic energy. All we've done is replaced K max with charge times stopping potential. So here's what I said just as a graph. This is the effect of brighter light. Notice the top graph shows really bright light with a high current. The bottom line shows dim light with a low current, but they are all the same color, so they have the same stopping potential. Intensity does not affect the stopping potential because intensity doesn't affect the kinetic energy. Only things that affect the kinetic energy affect the stopping potential. And here comes a great screenshot. You should screenshot that. That's going to be useful for you. And here's the effect of changing the frequency of the incoming light on the stopping potential. Photoelectrons emitted by higher energy light have greater stopping potential. It's harder to stop electrons if they've been released by high energy light. It takes more voltage to stop them. Here comes a screenshot. Screenshot that. Notice higher energy photons require higher electrons released by higher energy photons have a higher stopping potential.
Because they had more kinetic energy, right?
Here it is.
All right, so if we talk about a graph of kinetic energy versus frequency, you may see this on a test in class or something like that. If we're graphing this, the line that's not dashed, the nice solid line, does not start at the origin 0, 0. So let's talk about what that actually means. So in the photoelectric effect, when incident photons, aka photons striking the surface, they need a minimum amount of frequency, energy, to eject the electrons. So below F sub c, that's what we call the cutoff frequency or threshold frequency. There's a couple of different terms for it, I think. Below that, electrons are just jostled around. They're kind of bumping into each other, so on and so forth. But at or above F sub c, electrons are actually able to leave the atom. They're ejected. But one thing that I want to point out is if you were to trace backwards with that dotted line, would that mean that kinetic energy would be negative? Or is kinetic energy able to be negative? And the answer is no. So here's a screenshot that you want to take. All right, and moving on. So we knew from earlier that kinetic energy is equal to HF minus the work function. And if kinetic energy is 0 at the cutoff frequency, remember, you can't go into negative kinetic energy, so that's where you hit 0 kinetic energy. The cutoff frequency is just equal to phi over Planck's constant. And here's our big equation that you probably want to take a screenshot of. So again, it says the cutoff frequency is equal to the work function divided by Planck's constant. And the F sub c of the metal is determined strictly by its work function. Again, that's how much energy it takes to actually eject the electron. So let's write this one other way. If you remember from earlier, hc over lambda is equal to the work function. And again, there's that constant, h times c is equal to 1240 electron volt nanometers. And v is the work function.
All right, let's try a practice problem then. The critical wavelength, the cutoff wavelength for a given surface is 600 nanometers. With what maximum kinetic energy can electrons be ejected if 450 nanometer light shines on it? Now let's take this question apart. The light needs at least the minimum energy is the energy carried by a 600 nanometer photon, but we're going to shine more energy with smaller wavelength light. We're going to shine 450 nanometer light. That's smaller light with more energy. So the work function is clued into us by that 600 nanometer light, and we're shining 450 on it with more energy. Well, in this case, the work function is hc over 600, and the energy that we're shining is hc over 450, which comes up to a difference of about 0.7 electron volts. And that's the maximum kinetic energy with which electrons could be ejected from that material. So why does any of this matter? Why did we take 33 minutes of your time to talk to you about this story? It's because classical physics couldn't explain why no electrons were emitted if the frequency is too low. It just shouldn't happen. If the frequency is too low, but we make the light brighter, classical physics said it ought to work. We couldn't explain why the maximum kinetic energy doesn't depend on intensity. Increasing the brightness of the light should give the electrons more kinetic energy, says classical physics. Classical physics couldn't explain why electrons were ejected instantly. It makes sense if you think of this as collision. It doesn't make sense if you think of it as absorption of a smooth spectrum of energy. The only viable explanation was that Newton and Planck and Einstein were right. Light was a particle. Except Maxwell and Young and Debroglie were also right. Light's a wave. And that's a problem. Because it can't be both. Which brings us to the idea of wave-particle duality. And here, Here are some important things that you learn as a physics student. Thing number one, waves can't be particles and particles can't be waves. We know this. Waves aren't particles and particles aren't waves. And then you go to physics class and you're a second semester physics major and you're taking intro to quantum and your teacher says, hey, guess what? Waves are particles. Particles are waves. Deal with it. Like I said in the beginning, it was a false dichotomy all along. In our human experience, we want waves or particles, and sometimes things are just both. It's unintuitive, but physics is right. So we know how to calculate the energy of a particle. The mechanical energy of a particle, for example, is its kinetic energy plus its potential energy. The energy of a photon is Planck's constant times its frequency, or hc over lambda. We know how to calculate the momentum of a particle. Momentum is mass times velocity. We can calculate the momentum of a photon because it does collisions. We'll show you an example of a photon collision in a moment. The momentum of a photon is Planck's constant divided by its wavelength. Screenshot that. You're going to need that. The momentum of a photon, its oomph in a collision, is Planck's constant divided by its wavelength. So photons of lower wavelength carry more momentum. But momentum isn't energy. Momentum is a collision idea. That's a Physics 1 topic. You learned about that in Physics 1. Well, if photons can have momentum, particles can have a wavelength. The wavelength of a particle is Planck's constant divided by its momentum. Because if the momentum of a photon is Planck's constant divided by its wavelength, then the wavelength of a particle is Planck's constant divided by its momentum, where its momentum really is just its mass times velocity. Of course, the wavelength of a photon we're used to, that's the speed of light divided by its frequency. So wavelength is Planck's constant over momentum. It's called the de Broglie wavelength. Okay, so waves do diffraction because they have a wavelength. In 1927, Davison and Germer discovered that electrons do diffraction because they have wavelength, and that's weird. If you shine a stream of electrons onto nickel, just the metal nickel, those electrons exhibit diffraction. They exhibit maxes and mins. The electrons, the particles, those tiny pieces of matter with actual mass that are actually there. They ought to work like marbles, but they don't. They exhibit diffraction. Again, super weird. On the small scale, particles exhibit diffraction. They exhibit wave properties. We see it in double slit experiments using elementary particles. We can just do this now. We can send a stream of particles through a tiny gap and they diffract. They exhibit wave-like properties. And on the human scale, we don't notice it. You don't notice yourself diffracting, but do you have a de Broglie wavelength? Sure you do. Take Planck's constant and divide it by your momentum. Go ahead and do it. Waves can also exhibit particle-like properties. Photons, for example, have momentum. They have energy that relates their frequency and their wavelength. We are not going to make you solve this problem that comes up, but it's going to be one that you're going to want to screenshot. The idea is, well, Mr. Eaton, I'll let you explain what the idea is.
Well, the basic idea is you know what the energy of the electron is, and to find its velocity, all you need to do is use kinetic energy as 1/2 mv squared and solve for velocity, which gives you 5.62 times 10 to the 6 meters per second, kind of right in the center of your screen. Now, in order to find the wavelength, we just use a simple equation, lambda is equal to h over momentum. And since we just found its velocity, and we know what h is, which is Planck's constant, we can divide Planck's constant by its mass times velocity to give us a wavelength of 0.129 nanometers. Pretty straightforward.
And it's a small number, sure. 0.129 nanometers. 0.12 times 10 to the negative 9. It's 10 to the negative 10. That's a little number. but it's also a wavelength for a thing. That's weird. So the best example of light interfering with matter this way comes in a phenomenon called Compton scattering. In Compton scattering, a photon collides with an electron. Collides. That's momentum talk. The electron gains some momentum and the photon loses momentum because momentum is conserved. That's a big idea in physics. This is observed as an increase in the photon's wavelength. Now it matters because it cannot be explained if we treat light as a wave. So let's take a look. Here is an electron, that blue dot in the middle of your screen. Send in a purple photon. Note the wavelength, it's kind of small because the photon's purplish. The electron doesn't absorb the photon, the electron gets bumped around. It gets collided with. The electron gained momentum. It's moving now. The photon lost momentum, but look at its wavelength. Its wavelength got longer, it got bluer. There was a wavelength change. The momentum change exhibits as a wavelength change.
All right, so let's see what you can get out of what we just taught you. So in our guided practice today, we're going to answer 3 questions. The first one's about intensity of light and how it affects the photoelectric effect. That's a lot of effect words in there. The second question uses the work function to determine if an electron will be ejected. And the last is about the maximum energy of a photoelectron. Okay, our first question for today. When a beam of light is shined on a piece of metal, electrons are ejected from the piece of metal. Which of the following claims is correct about this phenomenon? I'll give you just a second to read it. Okay, I'm going to take some pretty quick little point outs here. The number of electrons ejected is going to increase. All 4 of those say increase. But I remember Mr. Mancino saying something about intensity. And I think the correct answer for this one is that the number of electrons ejected increases if the intensity increases without changing the wavelength. Because I remember changing the wavelength is going to change the energy, not the number of electrons. And there's our right answer.
All right. But what if we shine a gamma ray on a piece of foil with the work function of about 3 electron volts? Now there's the wavelength of a gamma ray, 0.2 nanometers. And the work function of ytterbium, 3 electron volts. What do you think happens? Does the gamma ray eject an electron because it has enough energy? Does it not eject an electron because it doesn't have enough energy? Does it eject an electron because its wavelength is comparable to the size of an electron? Does it eject many electrons because it has many times the work function worth of energy? Well, no, it doesn't do any of those. It passes through because you can't stop a gamma ray with a sheet of foil. That's from yesterday.
You're supposed to eat it, right?
Don't
Okay.
eat gamma ray emitting radioactive samples.
Yeah, just don't. Okay, last one. The maximum energy of photoelectrons emitted from a metal surface depends on which of the following. And if you paid attention during the first practice question, we would know that it's definitely not the intensity. But if I want energy, that's related to frequency. And the work function is something that takes away from that kinetic energy of the ejected electron. So 2 and 3 are the correct answers for this one. All right, and I actually lied. This is our last question. Okay, which of the following phenomena is an explanation that treats light as a wave most appropriately? So I've got 4 choices here. Visible light shining on metal has a minimum frequency to cause electrons to be emitted. That's the thing that we just talked about, photoelectric effect. B says visible light shining on a multi-slit grating causes an interference pattern. That sounds like from a couple of lessons ago. X-rays impart some of their momentum to an object. Momentum sounds very familiar to a Physics 1 topic. And lastly, X-rays incident on crystalline solids create a diffraction pattern. All right, so I'm going to point out the ones that are particle. Can you find them? So when we talk about particles, particles are definitely ejecting electrons, mainly because of that kind of like bumping nature. It's kind of the way we've been thinking about it. And the next one is the Compton scattering. So X-rays are scattered because mainly that says momentum. So that's the particle nature. So wave nature, though, is interference patterns. If you remember us shining a laser beam through a diffraction grating, it showed a diffraction pattern on the screen. And the last answer that's for a wave is a diffraction pattern again. So I've got interference pattern and diffraction pattern. Those are my two key words that point out that that's the wave nature of light.
All right. So how did we do today? Did you figure out that certain metals emit electrons when light shines on them, and that the energy from those photons is transferred to the electrons as if there were a collision, because there is a collision? Do you remember that the work function describes the amount of energy it takes to eject an electron? How about that particles have momentum and photons have momentum? But particles also have wavelength. On a small scale, matter has wavelength.
And can you answer these before you leave today? Does light behave as a particle, a wave, or both? And do you have a de Broglie wavelength? And how does the work function determine if an electron is emitted? These are tough questions.
Indeed. Physics is hard. Here are some AP exam questions you're going to want to screenshot. We're going to start tomorrow's lesson by answering these questions. So it's not a gamma ray anymore. It's UV light that shines on ytterbium, still has a work function of 3 electron volts. What happens? Take a screenshot of that. We'll start that tomorrow. And finally, monochromatic light shines on a metal like shown above. The frequency is varied and we make this graph. What's the physical meaning of the horizontal portion of the graph, that flat part of the graph, between the origin and the critical frequency? Why is it flat? And if a second metal were used with a different set of properties than the first metal, how might the graph look different? What could change in the metal, and how would that change the graph? Those questions will be answered tomorrow. So, hey, thank you so much for watching us. It has been a blast being your teacher. We can't see you. We don't know where you are, but, well, we together have a great big classroom. We hope you join us again tomorrow. Be sure to complete the practice question.
Thank you, everybody, for joining us. We'll see you tomorrow.